I'm going to start recording. And yes, I am recording now. So this is where we left it last week with this Is That It? What was that about? Well, we had seen in previous slides the description of that AI winter. After the very promising start for this newfangled AI discipline in the 1950s, there was a strong epoch of growth for the discipline in the 60s and 70s, 1960s and 70s. We are talking ancient history in terms of technology. And then there was this backslash when the technology failed to deliver in some of the, let's say, more optimistic promises. I want to take a second to think about why that happened. Why did the technology fail to deliver? Probably because the promises were non-realistic. And non-realistic promises do happen in academia almost by design. So, as a university professor, part of what you can do depends on funding, and that funding depends on research projects, which you have to write down, make a proposal, and then you send that to some government or some private institution or someone who receives many of those and has to decide who they give the money to, who they will allow to pursue their research project. So it's natural that there is a kind of a competition for the resources, which are in some countries very scarce and in some others always, well, less scarce, but there is never enough for everyone, let's say. So natural strategy is to just try to sell the strong points of what you're doing, of what you want to do as much as possible. And that naturally derivates into wild promises for some sort of technology. In an area like AI was in the 1950s, where things were growing fast and some interesting results were happening, it's only kind of natural that people would get ahead of themselves a little bit and start over promising. Okay. I think this is very clearly happening now. And I think the absolute oversaturation that we have these days with AI and with LLMs is a similar type of things. These huge companies, OpenAI, Google, Meta, also lots of Chinese companies like, for example, Baidu, which by some metrics is the leader in self-driving cars, which is another area of application of artificial intelligence today. All of these companies have spent lots of money, and the governments that support them or that relate to them have also a big stake in this technology actually succeeding. So people in these companies are under lots of pressures to try to deliver on the heavy investment that they have received. And that's what happened also in the 60s and 70s. At some point, some backslash is just to be expected. We mentioned some, let's say, philosophical and technological limitations that were uncovered and that triggered lots and lots of cutting of spending in AI at that time. That meant that an area that was very popular and was growing really, really fast suddenly saw its funding cut down, and it started decelerating and going slower. And to many people in the wider media, which is not as patient to follow technological developments as the people working in the area itself, it felt like that whole thing of AI was just something of the past, kind of a failed experiment. And we entered that big AI winter. And I was asking myself whether that was it, if there was nothing else afterward. Okay, and the short answer is no, and in part, that's why we are speaking about it today. But I do want to say one thing before I continue, that is that I strongly believe that we are heading to an AI winter, second AI winter pretty soon. I don't know how winter it will be. Maybe it will be just a bit of a chill. I'm not the only one saying that. Actually, it's a wide trend of prediction now because we have seen a huge epoch. We are seeing a huge epoch of growth for this new wave of AI products. And I think we have seen our share of wild overpromising too. So even though there are many, many good results, many, many interesting uses for the technology, probably there is going to be some backslash at some moment. Will that be very sharp and very severe, like what happened in the 60s and 70s, up to a point of more or less abandoning the technology, or will it be just a small deceleration while the thing keeps churning on? I do not know. I'm more of the first bent, but it's a little bit difficult to say at this moment. Okay. Okay, so no, that was not it. The advances triggered by the development of artificial intelligence in many areas kept coming. Maybe at a slower pace, maybe with not so big a splash in the media, but they kept going on. For example, 1979, we have the Stanford Cart experiment. That, in some respect, is the first autonomous vehicle, 1979. Okay? And it just moved inside of a room in Stanford University in the US. Nowadays, the huge advances in autonomous driving technology owe their existence to that cart, probably, and to other things, but that was probably one of the beginnings. And we are seeing that a technology today that started there and that might change our societies at a fundamental level. If cars start being autonomous and we start sharing them, probably we can ameliorate some of our pollution problems, some of our congestion problems in cities. Maybe we can build cities that are different because we do not need such expensive methods of transportation. Technology has the potential of altering our societies, and it has done throughout history. In 1990, TD Gammon reached world master level in backgammon, which is a game. Okay, and checkers, 1994, one human world champion resigned a game against a computer program, Chinook. In 1997, computers broke chess. Chess machine called Deep Blue defeated the then world champion, Garry Kasparov. Not any world champion, one of the most dominant world champions in the history of chess. A guy that legend says had won more than one match by just staring at their opponent until the other guy got so nervous because that very commanding, very extremely good player was looking at them very sternly, and the other guy just thought there was something that they hadn't seen and got so nervous that ended up bungling the match. Okay. So advances kept coming. In the 1990s, the development of web crawlers had a fundamental effect on the development of the internet. Roomba is from 2002, which is an autonomous robot that we still use today and which has actually changed the world in a very small way, but very pervasive way too. Developments in autonomous vehicles, autonomous robots kept coming, and in 2007, DARPA launched a challenge for autonomous cars in urban environments. Okay, from 2011 to 14, we saw quite a lot of development in all those personal assistants, Siri, Google Now, Cortana from Microsoft, and many, many smartphones ones, which used natural language to communicate with users. Those are a precursor of today's LLM bots. Okay. How intelligent were all of these software, all of these contributions to the field of artificial intelligence, because we see that computers could then play chess or talk to you about simple topics, communicate, understand what you were saying in simple sentences. But how is that related to what we consider intelligence? I want to use one of the most impressive feats achieved in that time, which was the 1997, the feat of Garry Kasparov by Deep Blue. Deep Blue was a computer that was purposely built by a very big computer company, IBM, and that was able to defeat Garry Kasparov 3.5 to 2.5 in a 6-game match. Okay. It's important to say that a previous version in 1996, 1 year earlier, lost to Garry Kasparov. So it was not, let's say, a blowout like another that we will see in a while. And this purpose-built computer used something called the min-max algorithm. Min-max algorithm has two main parts. One is something called an evaluation function, which is very important for us, so pay attention. And the second one is the searching strategy. The evaluation function basically looks at the state of the problem, in the case of chess, at a board, state of the board, where the white pieces are, where the black pieces are, how many of them there are, what relation they have between them, how they are placed, and gives a score. In this particular configuration of the board, let's say something like the probability of winning for black is 37%. Okay? It's not, let's say, universally defined truth or anything. It's just an evaluation. So the goal for this evaluation function is to rate how good a particular configuration of the board is. And it's based on how many pieces there are, what pieces are threatening, what other pieces, how much pieces can move, and things like who controls the center of the board, or where the hell is the king, because in chess the goal is to kill the other person's king. Okay. And we will say a little bit more about this evaluation strategy, but once you have one evaluation function, then you need a search algorithm too. Now that I know more or less who's winning and by how much in this position, what do I do? Okay. Then the min-max algorithm is really not that sophisticated. You see what moves are possible for you and you try all of them. And then in each of them, you reevaluate the board position and see what the other guy can do. Okay, and you do that for a certain depth. I move this and he will move that, then I move that other thing and they will move that other thing, and then you have a tree of possibilities where you can search. How big is that tree? Well, in chess, after some pruning of this tree of possibilities, on average, at each position between 25 and 40 moves are possible at each level, okay? And that gives us this combinatorics here. After one move, we have, say, 25 possible boards. After two, then each of them have 25 more, so we are 25 squared, and so on and so forth. 25 cubed after three moves. So this thing grows quite fast, okay? If we search to depth 40 at 1 game per microsecond, so we are evaluating one board very, very quickly, that would take 10 to the 90 years to make the first move if we were trying to search to a depth of 40, okay? The engineers at IBM basically solved this problem of this search space being big by brute force. They designed a type of chess-oriented chip that could do lots of computing of that evaluation function that they designed. And I will say a little bit more about how they designed it later. And then basically put lots of computation. They had 30 workstations and were able to do 25 to the 12 searches in per turn. Okay. And they could search a little bit more, extend what they call promising lines, so do a little bit of a heavily prone search after that, reaching a depth of things that I have looked into, even if not completely exhaustively, for up to 40 movements. Okay. Not only that, but they also programmed opening database and end of game positions too, and position algorithms. So basically, for the first move, they did not check all the possibilities of movements for the chessboard, but they, depending on the openings that people do, they chose one, or if they were playing black, they continued with the well-known list of moves. And at the moment when the play deviated from what's usually done, which the normal openings, then they started exploring the search space. Sorry. Before I move on to that, the evaluation function, they basically hired a team of 40 engineers who could program that were also chess grandmasters. The two worlds have a surprisingly high, well, not surprisingly, a high amount of overlap. So they not only built those purposely built huge machines that could check many boards, but they also got a huge team of people sitting down thinking about how to evaluate the board. And these people hard coded a set of rules. If the king is in this square, then that will give me +1 or -1, and then I will count how many of the other guy's pieces there are, and so on and so forth. So they did a very detailed human thought evaluation function. Okay. So the way Deep Blue managed to beat Garry Kasparov was by first hard coding lots of human knowledge, the library of openings, the library of closings, the evaluation functions with all that very long list of rules that chess grandmasters had agreed upon and coded. Okay, if you knew lots of chess, you could code evaluation function in the same way. If this happens like this, do it like that, and they were really good programmers too. Okay, but no artificial anything there, just people coding. And then the hardware to be able to compute that function really quickly for lots and lots and lots of board configurations, and that simple thing of I'm trying to minimize get the maximum gain in probability of victory for me and the minimum for the other guy, thinking that I'm going to always do the best thing and the other guy is going to always try to do the thing that is worse for me. That's the min-max search strategy. Okay, that's how they did. Was that intelligent? I would argue that not from any, let's say, general point of view. It was all very ad hoc. It was very impressive, an impressive feat of engineering and of thinking, but still not something that we would consider a computer thinking on its own. So no generalization power there. If we want to play another game, we have to throw away not only the evaluation function, but also the whole hardware, which is only targeted to chess. Okay. Moreover, chess is easy. Chess is definitely not easy, as anyone who has played chess knows, but in terms of computation, search space, chess is not a difficult game for modern computers. The branching factor is only 25 or 40, okay? And you can still write evaluation functions, let's say by hand. Okay. There are other games that are not as easy. For example, Go. Go is not that easy, and that's the reason why Go was never even gotten close to be broken by this wave of artificial intelligence. The min-max algorithms that had defeated chess, that had been able to play better than humans at chess, could not touch even club professionals in the game of Go, where the branching factor, where the possible move at every position is much higher. Okay, so that's where artificial intelligence was in the 1980s and 90s. So not dead, slightly unpopular, but still giving good results of this type. Okay. Was it only used for games, which is the most prominent example? Well, no. There were also something called expert systems, which is a very interesting development in artificial intelligence, where big companies assembled groups of experts and managed to do a little bit like IBM had done, incorporate the human knowledge of those experts into automatic processing pipelines and call that artificial intelligence. One example is medicine, where we get this type of systems to analyze, for example, these histopathology images. That is where artificial intelligence was at when I was starting my PhD, for example. Artificial intelligence was one tool that people use sometimes, and for some problems it was very useful, but usually it required huge teams of professionals in one applied area, and lots of programmers, and more than anything, a huge amount of data. So we are not talking, as today, a master's student gathering data for 2 months, but we are talking a consortium of universities gathering data for 5 years, and then a huge team of doctors doing the annotations for the same duration of time. And then you could get this type of expert systems that were very helpful and were very successful in a way. Okay. At that time, there was also a big movement to eliminate programmers. You might have heard that AI is doing all the coding today. Okay. I think Anthropic leadership is very prominent in that, and OpenAI people have also been saying that we do not need programmers anymore because AI is going to do all the coding. That is something that was already said in the 1980s and 90s, and there were companies based on selling code that could be done by computers themselves without human intervention or with very little human intervention. Okay. That turned out not to work so well, in the same way that I'm very confident that, let's say, anyone learning programming today is not wasting their time, but investing in something that will be useful for a long time. It will probably change a little bit, like it's changing continuously. All technology-based knowledge is, and if you do not evolve, you stop being useful. But I believe the roles of good programmers are pretty safe. They're going to be a little bit different, and probably who is a programmer is going to change a little bit. But programmers are disappearing is something that's been said for at least the past 40 years. Okay. The first time I did this presentation, it was 2016, I think. And when I was preparing it, I read previous sources, which you can see cited in the presentation. And I found very interesting the evolution of the open questions of AI. Sorry, this way. Okay. This gives you a feel of how quickly the technology has moved recently. Okay. So when I say that I find there are some limits and that I find there is some hype and that some things that are in the media are just stupid, is an opinion, but that doesn't mean that the technology hasn't grown and that the technology is not worth it. Okay, these are two different things. I do not think we are going to get the singularity anytime soon, or that we will have killer robots roaming the streets next year. But I do think that there are many useful things that this technology can achieve, has already achieved, and can achieve in the near future and in the longer term future. Okay. And to give detail of how this technology has evolved recently, when I found some previous presentation, the author who had done that in the year 2000, so now about 25 years ago, 26, was considering machine translation an open problem of AI. In 2000, AI basically could not do machine translation. And the author of that presentation basically wrote one sentence in English, translated it automatically to Spanish and then back to English, and saw what happened. Okay. For example, here, sentence was Austin police are trying to find the person responsible for robbing a bank in downtown Austin. Translated in Spanish as el policía de Austin está intentando encontrar a la persona responsable de robar un banco en Austin céntrica, which is more or less okay. And translated back to English as the police of Austin is trying to find the responsible person to rob a bank in centric Austin. So there is the to rob instead of for robbing, and the responsible person instead of person responsible, which actually changes the whole meaning, but the thing is not too terrible. But we see that it was not perfect. And as soon as things got a little bit more complicated, it got really messy really quickly. A Florida teen charged with hiring an undercover policeman to shoot and kill his mother instructed the purported hitman not to damage the family television during the attack, police said on Thursday. Is in Spanish, un adolescente de la Florida cargado con emplear a un policía de la cubierta interior para tirar y matar a su madre mandó a Hitman pretendido para no dañar la televisión de la familia durante el ataque. Limpia dicho el jueves. Italian speakers might already glean that limpia is something that means clean and has nothing to do with police or anything. Cubierta interior also is absolutely unrelated, and we even have Hitman here, which the translation system interpreted as a name, which is absolutely not. When translated back to English, the whole thing ended up as an adolescent of Florida loaded with using a police of the inner cover to throw and to kill his mother, commanded to Hitman, tried not to damage the television of the family during the attack. Clean said Thursday. So not even grammatically correct. The whole thing has no meaning, and there are a couple of words that have no presence in the original text and that no one knows where they come from. That's an example also, this limpia, for example, is clean, of a kind of hallucination, like we were saying the other day. Hallucination is a term that I think seeks to humanize and to push the narrative that these things are really intelligent on their own by anthropomorphizing them, by looking at them like people. That's not a very good word, but what hallucinations uncover is that at some point the data production process goes off the rails and ends up in some avenue that's not where it should be, and creating absolutely nonsensical parts of the output. And here is another example. Okay, that was 2000. When I visited this for the second time in 2018, things had already gone quite better. For example, in 2018, in Spanish, the same thing, the same text ended with a Florida teenager accused of hiring an undercover police officer to shoot and kill his mother instructed the alleged hitman not to damage family television during the attack, police said Thursday, which is pretty much good. There is some minor grammar incorrection, but it's decent and it's understandable, and there is no major problem like before. So from 2018 to 2000 to 2018, the whole thing had changed. And for big languages like English and Spanish, the whole thing had been, let's say, more or less solved. This is just an example. In 2018 itself, I did the same experiment with Catalan, my mother language, which is a much smaller language. And things were not so good. The same text in Catalan sounded: un jove de la Florida acusat de contractar un policia incriminat per disparar i matar la seva mare va instruir el presumpte hitman que no danyés la televisió familiar durant l'atac, va dir la policia el dijous. And you can see here again the hitman here, so something interpreted as a noun, and policia incriminat is one of examples of this inversion of noun and adjective, which messes up the meaning. Okay. The translation of that ended up being a young man from Florida accused of hiring an incriminating police officer. So that ever before changes the whole meaning of the sentence to shoot and kill his mother, instructed the alleged hitman not to damage family television during the attack, the police said on Thursday. So not absolutely terrible like the one before in 2000, but not good. And this was 2018, showing that not only do you need good technology and better algorithms, but you also need a sufficient amount of data. Smaller languages like Catalan, which has about 6-7 million speakers, anywhere near English or Spanish, was not, let's say, solved by 2018. I'm making a very quick presentation, okay? This is not a proper study, this is just some examples to show you what I talk about. In 2023, things had changed again, and Catalan was also succeeding in this text, in this translation test, okay? So in 2000, we had machine translation as an open problem. In 2018, it was more or less solved. And in 2023, and today too, it was solved to a higher level, even for smaller languages with less available data. Okay, because it's my opinion that it's not that the people in Google Translate had gotten more data in Catalan, but that the algorithms had gotten better. In particular, the difference between the 2018 and 2023 translation is probably that the one in 2023 used deep learning. And what is that deep learning thing? Well, we have this scenario where after that AI winter, artificial intelligence had established itself like a kind of slightly boring technology that worked but needed lots of data and kept producing results in several areas, but no one was too excited about it anymore, which is quite different to what we have today. There were small advances, like for example, in 2009, there was this establishment of ImageNet, a competition to classify images automatically. So they built this big data set with images, and each image showed an example of one particular class, one particular thing. One image showed a dog, one image showed a cat, one image showed a plane or a person. Okay, and we had this huge data set with millions of images, and I think something like nowadays 100,000 classes, 100,000 different things that can be in the images. And the goal was to have a computer process those images, train some model, and then once you give the computer a new image, it has to output the correct label. There is a dog here, there is a cat, there is a plane, there is a something. 100,000 classes. So probably dog is not one of them. Probably you have all possible breeds of dogs and so on. Okay, that was 2009. In 2012, there was a paper called Image Net Classification with Deep Convolutional Neural Networks by Chris Kefke and Hinton, for example. Subscriber 2. All of those people, if you are into artificial intelligence, are now very, very famous people. Okay, you have the some links here if you want to go deeper into this. That was important because before 2012 and that AlexNet network, the error rate for the computer algorithms competing in this ImageNet contest, classifying that ImageNet database, was something about in 26. 26 means something like 26 errors for every 1,000 images. Okay, the winner of the 2011 competition XRCE got something like 26 wrong out of every 1,000, which is great, but still very far from what came later and also from human performance. In 2012, using those convolutional neural networks, AlexNet achieved a jump of 10 points in just 1 year and had an error rate of 16.4. In 2013, we saw further degrees of 5 more points to 11.7. BGG, which is a sophistication of AlexNet, in 2014 reached 7.3. And GoogleNet, another evolution of the same type of network, 6.7 in 2014. When the whole thing hit the mainstream again was in 2015 with ResNet, that achieved an error rate of 3.6 images for every 1,000. The reason why this was notable was not only because there was a very clear trend of downward of improvement in the error rate, so less and less errors in the classification of those images, but also because the human error rate was estimated to be about 5 images for every 1,000. So in this very narrow problem of classifying images into its correct classes in a very huge type of data set, deep learning became better than humans in 2015 with this resonant network that we are still using today and that you will use in project number 3. That hit the mainstream because, as happens, this was an area where human ability, human performance was supposed to be safe. This was a problem that was considered pretty difficult to computerize, to automatize. The whole thing continued. 2016, the error rate went down to 3.1. And in 2017, everyone was under the human limit and they discontinued the contest and then moved to some other type of database. Okay. That was the presentation of deep learning into the mainstream by becoming better than humans at classifying images. But is that all? Again, can deep learning do anything else? Well, yes. Deep learning in 2016 also broke the game of Go. This guy here in the image is someone called Isedol, which is not a dominant world champion like Kasparov was, but was a very good Go player, one of the best in the world. Okay. And in 2016, and you have this documentary here that you can check. I will not spend time with it today, but I recommend that you do. It's in YouTube, open to watch for everyone. It's a little bit long and it's a little bit, let's say, Hollywood-like, but it's still fun to watch. But it shows how in a game that has a much higher number of movements, so the possible configuration of the board is something like 10 to the 700, where brute force search like was used for Deep Blue and to solve the chess problem is not possible. Google's DeepMind, well, now a subsidiary of Google, an independent company at that time, managed to defeat this this Lisedol character in a game in 2016 by 4-1. In 2015, they managed to defeat the European Go champion, which is a little bit like beating, I don't know, I'm going to be very unpopular now, beating Japan at the World Cup. It's a good team, but it's not, let's say, World Cup royalty in terms of soccer. But then in the next year, they were able to beat one player at the absolute best, like beating the current world champion, whoever that one ends up being. Okay. This was also done among a very huge media presence by hiring, by renting a whole hotel and having lots and lots and lots of press there to witness this match between the human and the Go playing machine. It was a very interesting match where the human still managed to scrap a point, but where basically they were obliterated by this AlphaGo machine. And there were some very interesting moments that I recommend that you have a look. Some points where the computer was able to find a very, very rare move that humans very seldom could see and was deemed to have been creative. I think that's an example, textbook example of anthropomorphization. The computer is trying to find the best possible move so that it wins. And if it finds a path in its huge search space that gives it a very huge advantage, it will take it. That's in its programming. That's not creative at all. But when we see something that we don't understand, we anthropomorphize it. We think, okay, this is like a person being creative, finding a strange way to succeed. Okay. And the video also contains some interesting points where AlphaGo doesn't play like a human player would. When a human player is winning by a lot, a human thing to do is to continue to try to crush your opponent. Once AlphaGo is winning, it starts making, let's say, conservative moves because it already knows it's winning and now it's trying to increase the probability of winning by at least 1 point. It doesn't need to morally destroy its opponent because it's not thinking about anything like that. It's just increasing the probability of winning. And if by playing conservative, the probability of winning by 1 point is higher, then it will not go for a lower probability of winning by 100 points. Okay. And finally, this thing where AlphaGo is deemed creative, humans can do it too. And Isidol managed to beat the computer in one of the games by also finding one of these very rare movements that gives one of the players a huge advantage. And that was called the Hand of God move. And again, very impressive feat of technology solving this huge problem. And I will tell you a little bit more about how it works in a second. But is that intelligent? Okay, let's first say how it works and then think about the intelligence part. It works in a parallel way to how Deep Blue worked, but with very important differences. First of all, it uses probability in its search. So it's not an exhaustive search, but it randomly chooses some paths and not some others, with some weights depending on the evaluation of the board. So the search is a little bit more sophisticated. And more important, the evaluation function is learned. It's not hard-coded like the blue once was. The evaluation function is learned from having a model and fitting that model by looking at many, many games played by humans. Okay? So that's the part that nowadays makes us think about current versions of artificial intelligence as intelligent, because we say that they learn. And they have all these parts that we call neurons. So because we liken their structure to the structure of our brains by calling its constituents neurons, and that we liken its adjustments of its network components to learning, then we again make them sound like humans and make ourselves think that they are really learning. Okay, so was AlphaGo intelligent? No, it was not. It feels like that because We called its parts neurons, and we called its setting of the parameters learning. But as we will see in detail, it's not. It does have a little bit of the wonder effect of we do not know exactly how each parameter is set, but this is somehow similar to how a car engine works. I have a car at home and I drive it sometimes, and I know how some of its part works. But for most of it, my car's engine is a bit of a mystery to me. So it's a little bit of a wonder that the whole thing moves and that it takes me from one place to another. That the fact that I don't understand how it works in minute detail doesn't mean that it's magic. In the same sense, the fact that many people don't understand how deep learning networks work in their smaller detail doesn't mean that they are intelligent. Okay? And we will say a lot more about that in the rest of the subject. Okay? Okay. And deep learning can do many, many, many more things. Okay? But um, I'm going to skip that part because this is getting a little bit long. So basically, I'm going to say that deep learning happened when it did because of the confluence of factors. Basically, these neural networks, that was something that had been invented before, okay, and it had been called neural networks with this very, very clear goal of anthropomorphizing thing and giving credence to the whole artificial intelligence idea. But basically, these are neural networks are just a way to express functions that are very flexible, okay? Models that have lots of parameters. We'll say a lot about that. This technology that existed that has an input, for example, an image, has lots of things that I have painted here as random colored things, and we will explain how those work too, and then produces an output. And this setup of all of those many parameters is called training. Okay, we will say a lot of training. Second factor that worked there was convolutional neural networks. And convolutions is just a simple technical trick where instead of having the components inside of the network be very big matrices, they are very small matrices that move over the input. Okay, and you have a link there that shows you an example of how that works. Instead of having every node in the network be as big as the original images, like neural networks originally were, some people thought, okay, maybe we could have small matrices that we slide over the input, and maybe that gives us better results, and it turned out that it does. But those are, as you can see, those back and forward again, those are originally from 1998, with Jan LeCun here, another very famous guy today, Hinton again, by the way. So what happened between 1998 and 2015 with ImageNet that used this CNN idea? Well, it happened that although the idea was there, the technology was not. And the technology, the CPUs, graphic board that nowadays are used by LLM and originally were used to play Doom or other games, made it possible to have networks that were convolutional neural networks that were big enough to start giving results in significant problems. So the confluence of the three factors of the neural networks with convolutions and with enough computing powers is what is resulting in this new wave of AI and this deep learning revolution, the deep learning evolution. Of course, data is also a huge part of it, okay? Now, deep learning can suddenly do what artificial intelligence was already doing, but doing much, much faster and much easier. As I said before, you no longer need a team of doctors from 7 different American universities to collect data for 2 years. one student can connect data for 1 month and get, depending on the problem, depending on how well the data is collected and annotated, there are caveats, but reasonably get some good results with deep learning. Okay, that's not a promise, but that's a possibility. Okay. Not only that, but some of the theoretical capabilities of these networks now work. And there are two of them called reinforcement learning and transfer learning. And you can see more about them in the video that I linked, but I'm going to stop about this now because this is running a little bit too long now. Okay, so let me stop here for a second and allow some time for questions. Okay, so as it looks like there are no questions at this moment, I'm going to do two things. First of all, I'm going to briefly talk about project number 3, which is already high time, and then I will dedicate the rest of the session to talk in detail about how we do deep learning. Okay, so project number 3 has a, well, kind of a complicated structure, as you can see here from the index. Basically, if you're a beginner, I recommend project number 3 in its regular formulation, and that one has 5 tasks. But apart from that one, there are also several alternatives. Okay, the regular formulation is about image classification, like I said, for ImageNet. We will have lots of images of different tree species, the ones that we have used in project number 2, and we will train a ResNet network originally to classify them into their proper class, species number 1, 2, 3, 4, 5, and so on until, what was it, 47? That will be the goal. Okay, and I will say a little bit more about it in a second. But there are alternatives. So if you don't like that particular problem or have already done that or are more interested in something else, there is the possibility of working object detection instead of image classification. Okay, or semantic segmentation. The alternative project number 1 has more, let's say, code support from this year because the course on WASM document analysis has quite a lot of details on how to create a network for object detection too. Okay, a faster RCNN network in particular. You can also do semantic segmentation if you're so interested, or even regression. So there are 3 different alternatives and you only need to solve one of them. Okay, so please do not ask ChatGPT to solve all of them because the whole thing will be ugly and ChatGPT will not be able to do it. Just focus on one of them and you will have to solve basically these parts. First of all, you will download some data, and for the regular version, that's the same data as in project number 2. In task 1, you will be asked to prepare the data in some way. In particular, in task A, and that's task 1 in the normal version, you will be asked to take the build ground truth function that you have already done, and I'm giving you a version here in case you have not properly solved it, okay? And consider the label image, and then this list from binary function that takes the treetop file and creates a list of centers for each of the trees. Then you will be asked to go for each center to its coordinates and read in the label image what species that center belongs to, and then in the mosaic, cut a square patch around the center. Okay. In task number 1, you're asked to do exactly that. And here is a detailed discussion that we can review in some detail next week, but that you can already do. So if you haven't yet, please start with task number 1 and do your best. Okay. You need to receive an input folder, create a label image with the function that you already have, build GT, read the coordinates with list from binary, the coordinates of all the trees, of the centers of all the trees, and then create a patch around every tree and store it to disk. There are some details about the type of names that you have to put or that I recommend that you use, because those will be important for task number 2. This is where you have to do the most code for project number 3. This is the easiest code, but you have to do quite a lot of it. Okay, some code to test it. In task number 2, you will be asked to create a PyTorch data set. We will say a lot about what PyTorch is, and please be aware that you have this notebook here that uses a kind of code that you can more or less copy as it is. You only need some adaptations that we will detail later. Okay, so that's the presentation of project number 3. I recommend that you start doing task 1. You can choose the formulation that better fits your level and your goals in your master thesis if you're going to use deep learning for your master thesis, and then get cracking with task number 1. Okay. I don't know if there are any questions at this moment. No? Okay. Then I'm going to use these 20 minutes that I still have to speak about how to use deep learning in your own research. We have seen that deep learning can be very useful, and I want to tell you a little bit about how exactly it is used. There is a notebook. There are quite a lot of them, but there is one that's aimed, let's say, at absolute beginners, about how AI cannot count, and that uses some of the ideas that we will express now. There is also another one that I will hopefully get to use during the presentation now, that's about deep learning and computer vision basics, about how to feed models to data. And that's probably the most important thing that you have to learn. So I would recommend listening to the presentation now, maybe checking the video about how to do deep learning later, and then have a good look at this simple model fitting using PyTorch. This is not deep learning, but this is the basis of deep learning. Okay, I will read this notebook in detail when I talk about task number 3, but you can do it now and it will give you a good starting point. And then for how datasets are used and the things that AI can and cannot do, you can have a look at this checkerboard classification notebook too. How do we use deep learning? Well, basically, as we said before, we have this input and we want to get some output out of it, and we want to automatize the problem. In this case, we have an image defined as a matrix of pixels, like we have seen, that contains a patch of a tree, like you will do in project number 3. In this case, the problem that we want to solve is to classify our patches into 3 classes: healthy tree, sick tree, or dead tree. And this one contains a sick tree, the foliated fir tree in Zao, and we want to check. We want to build a system that automatically tells us that that image has a sick tree. We will pass the input through a deep learning network, and we will output, hopefully, the correct code, 0 in this case, for example, for sick tree. By the way, the reason why this part of artificial intelligence is called deep learning is just that these networks that we are going to use are grouped into layers, which is a little bit what I wanted to show here with the colors. And deep learning networks have more layers than original neural networks. So they are deep in the sense that they have more layers. There is no more to it than that. What is one of these networks? What does this represent? This basically represents a model. And a model is just a function with many parameters. We want to fit our model to the data in what we call the training process, or what we say that the model is learning the data using examples of the data with the correct annotation, and we want to see how well that worked with testing. Let me go to the notebook for this. This is the same as when we do linear regression. Okay, so you may or may not remember linear regression. This was not authored by Google. It was authored by me, so I can execute it. You may or may not remember linear regression, but basically you have some data and you want to, some data expressed as 2D points, and you want to fit a line through them so that it's as close to the points as possible. And the trick is in defining what fit means, what as close to means, and so on and so forth. And here I've done a very simple notebook that uses PyTorch to feed data to models, initially models to do linear models to do linear regression. Okay, what is PyTorch? PyTorch is just one more library from Python, one that does deep learning. Its main module is called AutoGrad, which basically means auto gradient or auto derivatives, because the main driver of all of this artificial intelligence deep learning revolution is computers doing derivatives of functions very fast. One of the best courses out there for deep learning is something called Fast AI. I think now they are changing the name, something by Jeremy Howard at the University of San Francisco. And the motto of the courses is something like making neural networks uncool again. Artificial intelligence is surrounded by all of this mystique, but most of what makes it work is just very basic math. And in this case, we will see some of that very basic math. First, we define a function, and you can have a look at it, to generate polynomial data. We decide a list of coefficients, and if I only have 2 coefficients, so degree 1 polynomial, I generate some linear data. If I have 3 coefficients, then that's degree 2 polynomial, and I get some sort of quadric, and so on and so forth. 4 coefficients, degree 3 data, I'm creating points around cubic with some noise added. Okay, so sorry, here after generating the linear or whatever the polynomial data, I add some random noise so that it's not a perfect line, quadratic, cubic. I could do degree whatever I want. Okay, if I if I do 7 here, then I will have degree 4. Okay, which is not shown very nicely because I haven't shown everything, but believe me, if I open the axis, this is going to be degree 4, and it's going to be prettier. Never mind. I have defined my data. Then I also define what it means to be close. If I fit a line through here, what will it mean to be close? Well, I implement something called the least squares, which means that for every value of my model of my line, I will consider the x of one of the points, and then the predicted value for my model will be the point of the line that's in this same x coordinate. Okay, so and how far away to the square that predicted point is, that point in the model, the predicted point is to the actual real data, that will be the difference. Okay, so least squares. Consider the data points, consider the model, and then the distance, Euclidean distance from the real point to the point in the model to the predicted point will be my difference. This is called least squares, and it's very, very widely used. And now we need to define a model. Okay, a model is just a function. So for linear regression, we define a linear model with this very simple linear equation. Y equals ax plus b. High school equation of a line, parametric equation, implicit equation of a line. Okay, so we can define this model, and then we can just plot a line that we have defined with random coefficients. So I just choose a couple of coefficients, and then I plot my linear data with a line there somewhere. Okay. Then what I want to do is to fit my model to my data. So basically, I want to change the position of this line so it's close to the points, as close as possible to the points as defined by the least square things. Okay. And to do that, what I do is fit it. This is the training. This is the learning in deep learning. Okay. What does fit do? Well, I basically do a series of iterations, which I will call epochs, which is a word that you might have heard in deep learning. So for a certain number of epochs, what I do is that with the position of my model, I make predictions. So the prediction for x equals 0 is here. This is where I predict my data will be. Is it close? Well, not very. It's quite far away. Okay. So for every position of my model, first I make predictions for all of my data. Then I calculate the loss. First I see where my prediction is, and then I see how far from the actual data that is. Okay. And then I have a final step where I use some optimizer to change my parameters of my model so that it moves and it's closer to the data. Okay. So basically, the distance from my model to the data is what I call the loss function. I want to make that loss function as small as possible. So what I have is just an optimization method to compute the minimum of the loss function. I have my data, I have some position of the model determined by its parameters, and then I have the loss function, and I want to make the loss function small. I want to change the parameters of my model so that the loss function keeps going smaller and smaller and smaller. Minimum values for functions are computed using the first derivatives, the zeros of the first derivatives. The places where the tangent is flat mean that I either have a maximum value or a minimum value, and I'm looking for minimum values, so I need to find the zeros of the derivative of the loss function. And that's why PyTorch main module is called AutoGrad, because it computes those derivatives of this loss function very quickly. And then I use some optimizer to generate the new set of values and try again, and do that for as many epochs as needed. Okay. See that first I make predictions, so I use my model as it is. That's called the forward step. And then I need to compute the derivative of the loss function. The derivative of a function uses the inverse of the matrix that represents the function. Okay, you might have seen that from numerical computation if you have ever done numerical computation. If not, just believe me, in order to compute derivatives, I need the inverse of the matrix that represents the function. And that's why this step where I compute the derivative and then use it to generate the new version of the parameters, the new values for the parameters, is called backward. Making the prediction is called the forward step. Generating the new sets of the parameters from the values of the derivative of the loss function is called the backward step. Okay, and this scheme for a number of epochs, make predictions, calculate loss functions with the forward step, and then use the backward step, derivatives and so on, and then compute the new set of values with the help of some optimizer. Predictions forward, backward. That's the optimization function for linear regression or quadratic regression that we can also do here, but it is also the fit function for deep learning networks, as you will be able to see in the patch classification notebook that I mentioned earlier. What we do with deep learning is fit models to data. In this case, you have all the details about how to fit. We do that, we run it, and then our line gets closer to our data, how to fit a linear model to some very simple data. And if the data stops being, you have a nice video here, which shows you how the optimization process works, okay, and how the line goes nearer and nearer to the data, okay. This is just a part of it. Have a video that we can watch in YouTube because it's not working anymore here, where, sorry, the animation is a little bit quicker and we see the model going to the data a little bit faster. Faster in the initial steps, a little bit slower later. And that's also a characteristic of when you train deep learning networks. So if you get stuck in a local minima at the initial steps, then you probably cannot get rid of that and cannot move past that one, okay? But basically, we are just seeing, I posted, the model get closer and closer to the data by that process that I said. Make predictions, use the forward to make those predictions, the forward step to make those predictions, use the model as it is to make the predictions. Second step, compute the derivatives in the backward step, and then generate the new set of values and iterate, okay? That's how you use PyTorch to fit linear models to data. And if we change the model and because for example, if we have quadratic data, there is no way in hell that we can fit a line to that, then we can just define a quadratic model in the same way as we did. Now this one, instead of having 2 parameters, it has 3, A, B, and C. And now we can use the exact same fit function to fit quadratic, cubic, any polynomial model. Not only that, we can use a very similar fit function, not exactly the same, but basically the same to the fit function that I defined earlier, very similar function to fit deep learning models that are nothing else but more complicated models. So they don't have 2 parameters, 3 parameters, they have millions of parameters. But most of those parameters are still linear, are still matrices. They contain some non-linear things. We will say a little bit more about that, okay? So when we do deep learning, we consider we're essentially doing the same as with linear regression, but we have a function, a model that have many parameters. there is something called the universal approximation theorem that sounds very amazing, that says that with a deep learning model, I can solve any problem. That sounds great, but what it actually means is that these type of functions that we use in deep learning networks are very flexible. So if I have enough data, and if I have good enough annotations, and if I have enough time, then yes, I can probably solve any problem or go as close to the solution of a given problem as I want. What does enough data and good enough annotations and enough time mean? Well, it depends. And for one particular problem, it might be the data that I can collect within my master thesis and a couple of minutes to train a normal model with the annotations that I can do in a few hours. And for some other problems, enough data might be more data than I can ever collect. Okay, so this just means that the functions are flexible, not that they will provide solutions. Okay. This setting up of the parameters of one particular model is what we call the training step. And then we also want to check how the model works, the testing step, which is something different. Okay. We spoke about the model, we spoke about the training, and we spoke about the loss function. Okay. We will see examples to finish this presentation today. And this is from one paper that we published in 2021. Given the same images, we can define different problems here. And those are, some of them, you have them in the different alternative version of the project number 3. For example, one of them is classification. I have an image and I only want to assign one label to that image, in this case, the species, Pterocarya riofolia. Okay. Maybe I want to do classification and localization. So I want to not only say what's in the image, but exactly where. Maybe I want to do semantic segmentation, where I assign to every pixel in the image one label, one category, the Pterocarya riofolia category, and then I have bush, which is in green, and soil, which is in yellow. Okay. Or I want to do object detection. I want to find not only, I want to find what's in the image. So for example, this is Cryptomeria japonica, and this is Pisceavis, and so on, Castanea crinata. And then I also want to put boxes around them, or even more than that. That's called object detection, and there is an alternative version in the project 3 about that. Or I want to do instance segmentation, put the boxes, but also segment exactly what pixels belong to each instance. Okay. Okay, let's leave it here. We saw a little bit more about the history, and we presented a little bit more about how deep learning is done. Go have a look at task 1 from project 3 to see what you have to do to prepare. Go have a good read at the 2 notebooks that I mentioned to see exactly what this model training means. And then in the other one, you will have another example of model training, but you also will have some data sets, which will be a big part of what we explain next week. Next week, I will explain a little bit more about the practical implications of how we do deep learning and what problems and what things happen. And I will talk about training, validation, and testing data sets, and a lot about PyTorch data sets. Thanks everyone for listening.
Thank you.
Thank you.